Hello, welcome to Paradox's Sunday School class. Good day to you. This is September 25th, 2022. Dr. Ross is here today. He's going to be speaking again on the miraculous super galaxy clusters. He'll be here next week speaking on 1 John and how to prepare new Christians. For those of you in the cyber world, look online at paradoxes.org and get into the chat if you have questions. We welcome questions. And with that, Dr. Ross, please come up.
Well, it's good to be back with all of you here. I mean, it's been 2 weeks. I've been in Hawaii teaching at Anchor House. I gave 14 talks there to a group of young people. And there are people who are signing up for a 9-month program where every week they get to hear from a Christian scholar from some part of the world. And so it's a privilege to talk to them and really equip them. And it was a bit of a culture shock. I was the first one to actually give a set of lectures for them. I've not been raised in a Christian home. I didn't really meet Christians until 8 years after I became one. I'm a Gideon convert. But the audience I was addressing there in Hawaii, 100% of the students there were raised in Christian homes. The majority were homeschooled, and none of them had really had any experience outside of the Christian community. And so I was there basically to equip them for ministry, to bring people to faith in Jesus Christ. So it was a pleasure to be launching the Anchor House program. It's basically patterned after Cape and Ray, where they have students for 9 months. They hear lectures from these scholars around the world, but they also get to put into practice what they're learning literally while they are there. But while I was in Hawaii, I began to work on this series I'm doing, our supernatural galaxy, looking at our galaxy. Yeah, we did talk about our galaxy cluster, but looking at our galaxy, it was literally on the flight home I realized I missed something when I wrote the book Design to the Core. So what I'm going to be sharing with you this morning is something that pieces of it are in the book, but the apologetic link wasn't really fully made. I'm going to share that with you this afternoon actually. And all of you who are watching online, again, I commend to you the book Design to the Core. But I'm going to give you a little bonus that's not in Design to the Core. And the theme we kind of launched off with this series on our galaxy is that if you were to see a roll of the dice 16 consecutive times coming up snake eyes, what would you assume about the dice? Would you assume the dice was just a random thing, or would you realize, no, this is a pair of dice that's been weighted to always come up snake eyes every single time? Well, the same thing is true of our Milky Way galaxy. And this is part 3. So if you've missed part 1 and part 2, they are video archived at paradoxes.org. So you can download it for free and watch the video, or if you just want to listen to it while you're driving, you can also listen to the audio. But we're been examining these past 2 times I've been here with you, the amazing features of our Milky Way galaxy, how there is no galaxy like it. I wrote a book called Improbable Planet. I could actually write a book called Our Improbable Galaxy. And one of the things we did 3 weeks ago was look at those spiral galaxies that come the closest to matching our Milky Way galaxy and having the necessary features that would make advanced life possible. But as I shared with you 3 weeks ago, we astronomers have looked at tens of thousands of spiral galaxies. We've only found one that has the characteristics that would permit the existence of advanced life, and that's namely our own. And I shared with you briefly a side-by-side comparison of our Milky Way galaxy with the spiral galaxy that comes the closest to matching our Milky Way galaxy in permitting the possible existence of life, and that would be UGC 6093. But a couple of the differences, Its spiral arm structure is more than twice the diameter of ours. And it has a much higher ratio of stars to dark matter than is the case of our Milky Way galaxy. In our Milky Way galaxy, only 0.45% of its total mass is in the form of stars. What's typical for other spiral galaxies, somewhere around 10 to 15%. So that's one of the unique features of a Milky Way galaxy. The spiral arm structure is small, the number of stars is much smaller, and has far more dark matter than is the case. And with UGC 6093, it has a supermassive black hole that is almost 7 times more massive than the one in our Milky Way galaxy. And you do see some similarities. You do see that the spiral structure is similar, although the Milky Way galaxy has very symmetrical spiral arms, where you do see that there's been some distortion from past merging events in the case of UG 693. Notice that the barred core is roughly shaped the same, although if you look carefully, you'll see with UGC 6093 that the bar feature is dimmer and smaller, and the core is much bigger and brighter. And that's because the supermassive black hole there is pulling in a lot more matter. Matter of fact, UGC 6093 is classified as having an active galactic nucleus, and also has what's called a megamaser. I won't go into the technical details, I covered that 3 weeks ago. Bottom line, an active galactic nucleus means that the galaxy's supermassive black hole is pulling in so much matter that that matter is being converted into radiation that's deadly for life anywhere within that galaxy. So not only is this galaxy not a candidate for advanced life, it's not a candidate for any kind of life at all because of the activity going on in its core. And I closed out 3 weeks ago by making the point that one of the features that must be fine-tuned for advanced light to be possible is what's called the spiral arm pitch angle. And that's the angle of the spiral arm relative to the tangent to the circle surrounding that particular case. And in our Milky Way galaxy, the pitch angle is 13 degrees. Make it 11 degrees or 12 degrees or 14 or 15 degrees, and then you wind up with having a spiral arm structure that eliminates the possibility of advanced life. Not necessarily the possibility of microbes, but the possibility of advanced life. The smaller the pitch angle, the more tightly wrapped are the spiral arms. And it's crucial that the spiral arms are fine-tuned distance apart from one another for advanced life to be possible. Now, when we astronomers look at spiral galaxies, and if you recall from 4 weeks ago, I was making the point, if you want to have a life in a galaxy, it has to be a spiral arm galaxy. The vast majority of galaxies, the spiral arm structure is collapsed, and you have what's called a spheroidal or ellipsoidal galaxy, where now the stars are far too close together to have a planet orbiting a star, where you get a stable planetary orbit, or have that planetary system isolated from stars that are pouring out deadly radiation. Spiral galaxies will space the stars far enough apart where you can avoid those gravitational disturbances and the radiation. But as we astronomers look at these spiral galaxies, they fall into 2 categories. We got the blue galaxies and we got the yellow galaxies. And blue is the color of fairly young stars. So when stars first form, they tend to burn very hot, and the hotter the star, the whiter or the bluer the color, and then the dimmer the star, the yellow or more red the color. And so stars that are filled with young galaxies have a blue color. Stars that are filled with old stars have a yellow color. And so we can classify spiral galaxies as blue or yellow. Our Milky Way galaxy is classified as a green galaxy. Now, it's not really green. I put green in quotes, but what they mean by green is it's a balanced mixture of young and old stars. Some of the stars are yellow, some of the stars are blue, and yeah, if they were completely mixed, the galaxy would take on a green color. And green galaxies, green spiral galaxies are rare. So typically, spiral galaxies are new form, and the reason why we see this with our Milky Way galaxy is that it's still bringing in gas to form new stars, but bringing in gas, as I mentioned 4 weeks ago, through these tiny dwarf galaxies. And as we zoom in on the spiral structure, and again, this is review. You can download from paradoxes.org and get the details. But as we zoom in on our local neighborhood, you see that we are located on the inside edge of the local arm. We're not right on the local arm, we're on the inside edge. And if you look carefully at the zooming in a little more, you notice we're on the best side of the local arm edge. If we were on the far side, we would be in a denser part of the local arm and hence subject to more gravitational disturbances and radiation. But we're on the inside part of the local arm. The local arm, you can see, is actually an offshoot of the Perseus spiral arm. If you go back along it, you can see where it connects with the Perseus spiral arm. And so the local arm is situated between the Perseus arm and the Sagittarius arm. But because we're on the inside edge of the local arm, we're actually closer to the Sagittarius spiral arm than we are the Perseus spiral arm. But what you notice here is that as we look towards the Sagittarius spiral arm, we're looking towards the least dense part of that arm. So the closest part of that arm to where we are is the least dense part of the Sagittarius arm. And notice how much more predominant the Perseus spiral arm is. And yeah, you don't want to be too close to all the big gaseous nebulae and dense star clusters in interstellar clouds in the Perseus arm. And that little circle there that shows our sun, that's actually roughly the size of what we call the local bubble. And so we're in the local arm, and we're in what's called the local bubble of the local arm. And you say, what is the local bubble? It's a bubble of gas, but it's gas that's underdense. So we're in an underdense region. The local bubble describes a sphere which has a paucity of gas, dust, and stars. And it's that lack of gas, dust, and stars that protects the planets orbiting our star to be protected from gravitational disturbances and radiation. Now, I want to focus most of the rest of my time here by looking at the structure of the local bubble. So this is new material. So we're going to zoom in on one of the more detailed maps astronomers have produced of the local bubble. And everything you see white there is part of what we call the local bubble. It's about 1,050 light years across. So it's quite big. I mean, when you think that the Orion Nebula is 1,500 light years away, the local bubble is almost 1,100 light years in diameter. Now, what is in the book Designed to the Core is that the local bubble began to form about 6 million years ago, but it took 3 million years to fully form, and its formation was not complete until 3 million years ago. And so for the last 3 million years, we've been in this structure called the local bubble that's looking like this map that you see here. Again, it's 1,050 light years in diameter. It's a bubble of warm, very low density interstellar gas. And it's this local bubble that isolates us from dangerous gravitational disturbances so that our planet Earth, for example, can safely orbit about our sun, and it protects us from deadly cosmic radiation. And this is crucial that we be protected from this deadly cosmic radiation. And I think 3 weeks ago, when I was with you, I shared briefly this graph with you, which is making the point that for advanced light to be possible here on planet Earth, our planet needs to be super endowed with elements heavier than iron. And there's really only one place in our Milky Way galaxy where the density of these metals is high enough. And so this basically shows you, going out from the center of our Milky Way galaxy out to the outer edge, the abundance of these metals that are heavier than iron. And you see it reaches a peak about 4 kiloparsecs out from the center of the galaxy. And hey, if you want me to translate that for you, 1 kiloparsec is 1,000 parsecs, where 1 parsec is 3.26 light years. So we're basically talking about 13,500 light years out from the center of the galaxy. And that's where these metals are sufficiently abundant that you could get a planet that has enough uranium and thorium, enough lead, enough of the elements heavier than iron. However, if we were to remain there, that's the most dangerous part of our Milky Way galaxy. You've got big stars there that are going to be disturbing the orbits of planets around stars, and that's a region where you've got supernova exploding. That's where you got these big stars pouring out these heavy metals. So it's the most dangerous part to be. You want to be in a place that's safe. And that second dotted line you see there, a little more than 8 kiloparsecs out, or 26,000 light years. That's a safe zone where the abundance of these metals is at a minimum. But what astronomers began to recognize 2 decades ago, to explain the possibility of the mix of elements that we have that make our advanced life possible, our solar system must have formed at that first dotted line. The most dangerous part in our Milky Way galaxy got ejected from that after it was enriched with these heavy metals and wound up resting in one of the safest spots in our Milky Way galaxy. And so we need to form in a very dense region, a very metal-rich region. That's where we need to form, but we need to end up in a very underdense region where the density of these metals and the density of supernova eruptions is at a minimum. And this kind of shows you a map of our Milky Way galaxy, showing where the sun was when it first formed and how it got ejected from that and wound up where it is right now. And again, as I mentioned 3 weeks ago, the ejection took place as a result of our sun having a gravitational interaction with at least 4 supergiant stars where it got kicked out. And if you want an analogy, think of how NASA sends a spacecraft to Uranus or Pluto. What they do is they time the spaceship launch so they can get a gravitational assist from Mars or Venus and Jupiter and Saturn and get it out there so they can get there faster with less fuel. Well, the same thing happens here, is if you get the right alignment of big stars, you can actually get our sun and its system of planets being ejected from its birthplace and sent out. But in order to settle down, it needs to have a second gravitational interaction where it puts the brakes on the outward movement. And so you need 2 highly fine-tuned events. An event that ejects the solar system after it gets enriched with these heavy elements, and then you need a second fine-tuned event where a grouping of stars actually puts the brakes on the outward movement and has the sun settle down into the safe zone. But the bottom line is we got ejected from the most dangerous part of our galaxy, a crucial part where we got the necessary enrichment, and we ended up shortly thereafter in the safest part of our galaxy. And that annulus you see there, that red annulus, it represents what astronomers call the co-rotation distance. And the stars in our galaxy all obey Newton's laws of motion. And I don't know whether you remember this from your junior high science class in junior high, but Newton's laws tell us that a planet, for example, will take more time to orbit around its star the farther away it is. So for example, in our solar system, we see that Mercury orbits the Sun about once every 90 days, Venus about once every 280 days, Earth once every 365 days, and in the case of Mars, it's about 2 years. So the farther you go out from the star, the longer it takes to go around. The same thing is true of the stars in our Milky Way galaxy. Stars that are close to the center of our Milky Way galaxy will orbit about the center of the galaxy much more rapidly than stars that are farther away. If you're wondering what the galactic year is for our Sun, it's about 250 million years. So it takes about 250 million years for us to make one trip around the center of our galaxy. And so that's the behavior of stars. But the spiral arm structure behaves like a rigid disk. And so the stars take different times to revolve around the center of the galaxy, but the spiral arm structure behaves like a rigid disk. And the co-rotation distance is the distance from the center of the galaxy, where a star will take just as much time to revolve around the center of the galaxy as will the spiral arm disk take to rotate about the center of the galaxy. And one of the advantages of being close to the galactic zone, the co-rotation distance, is that means that you're not going to be crossing spiral arms very often. I'm trying to avoid the bright light there. Is this better for you on this side? Okay, I'll try to lean more to this side. So because we're close to the co-rotation distance, we do not cross spiral arms very often. And crossing a spiral arm is okay if you're a microbe. It's not okay if you're a human being. Because when you cross a spiral arm, you're going to be engaging giant molecular clouds. You're going to be engaging star clusters. And this is going to, again, induce gravitational disturbances. In fact, every time our solar system crosses the spiral arm, the comet and asteroid belts get disturbed, and our planet gets bombarded with asteroids and comets. So you don't want that happening when you got New York City and London on the surface of the Earth. You don't want them being bombarded all the time. But right now, we're halfway between spiral arms. Now, the one caveat is you do not want to be exactly at the co-rotation distance. If you're exactly at the co-rotation distance, that means you're going to have a mean motion resonance that's going to kick you away from the co-rotation distance, either outward or inward, and now you're going to be back in a dangerous zone. The best spot to be is on the inside edge of the co-rotation distance, which means you will cross spiral arms. You won't be permanently protected from crossing spiral arms, but now we're talking about crossing a spiral arm about once every billion years, as opposed to once every 30 or 50 million years. And so that's where we are. We're on the inside edge of the co-rotation distance. And if you're worried about the next spiral arm crossing, that won't happen for another 500 million years. We're halfway between. We crossed it just before the Cameron explosion, and we'll be crossing it sometime in the future as well. The galactic habitable zone. Now, as I mentioned, most of the galaxies in our universe are not spiral galaxies. In the present universe, about 6 to 7% of all the galaxies are spirals, and of those spiral galaxies, only a tiny percentage, 1 or 2%, are the appropriate size where you could have advanced life, because if a spiral galaxy is too small, it'll be gravitationally disturbed by nearby galaxies. If the spiral galaxy is too big, it's going to have too big of a supermassive black hole. Our galaxy is just right. It's the just right size, not too small, so it's going to be gravitationally beat up, but not too big where it's going to have too big of a supermassive black hole. But in the present universe, as opposed to the universe that existed 10 billion years ago, only a few % of the galaxies are spiral galaxies. The vast majority of galaxies are either irregular galaxies or they're like this galaxy, which is referred to as a spheroidal or an ellipsoidal galaxy. This is M87, one of the larger galaxies in the Virgo cluster. We're actually part of the Virgo cluster of galaxies, but we're on the outer edge of the Virgo cluster. This galaxy is 53 million light years away. Now, as you look at this image, you may be thinking you're seeing stars of M87. You're not. Those things that look like stars are globular clusters. You say, what's a globular cluster? A globular cluster is a dense cluster of stars where the cluster is maybe anywhere from 3 to 20 light years across and contains anywhere from 10,000 to 10 million stars. So it's a very dense grouping of stars. And literally every dot that you see on this image is a cluster of tens of thousands, if not millions of stars. So, and to give you a point of comparison, this particular galaxy, astronomers have counted so far, it's not a complete list, but they detected so far 15,000 globular clusters. And again, multiply each of those by, say, 100,000 to a million stars. By comparison, our Milky Way galaxy has 152 globular clusters. This has more than 100 times as many globular clusters. And this galaxy was a spiral galaxy. Probably what happened is 2 or more spiral galaxies collided with one another, and the collision caused all the spiral arms to collapse and become this dense grouping of stars. Some other characteristics, 1/6 of the mass of this galaxy is made up of stars. And in the comparison of our Milky Way galaxy, 1/200th of it on the mass of our galaxy is stars. In this case, it's 1/6. And the stellar envelope, so if you look at what you see, that bright glow of a globular clusters in the galaxy, it's about 50% bigger than our Milky Way galaxy. So its size is 50% bigger, but its mass is 200 times bigger. So it gives you an idea just how jammed together the stars are. And again, this makes up about 90% of all the large galaxies in the presently existing universe. Now, these are dangerous not just because the stars are too close together, but when you've got stars that close together, we wind up getting a really big supermassive black hole. Our Milky Way galaxy, the supermassive black hole, is about 4 million times the mass of our star, the Sun. In this particular galaxy, 6.5 billion. And because of that huge supermassive black hole, it's actually radiating out a jet of very deadly radiation. I think you can look carefully there and you can see the jet off to the right. I'm going to zoom in a little more so you can see it a little more easily. Okay. And then this is looking at the core. So here you see the core in the upper right. That's where the supermassive black hole is. And that's a jet of cosmic radiation coming out there. And the radiation coming out from M87 is so intense, it not only makes life impossible in that galaxy, it makes life impossible in all the galaxies around it. Fortunately, we're far enough away. We're 53 million light years away. That's far enough away that the radiation is not a problem for us, although it would be if that jet were pointed anywhere near our direction. Fortunately, the jet is pointed away from us. So even at 53 million light years away, if that jet were any closer to us, pointed any more directly towards us, we'd be in trouble. And I think it was about a year ago, I shared with you how astronomers have actually pulled together radio telescopes from around the world. I'm a radio astronomer. Why I went into radio astronomy? When you're in optical astronomy, all you get is the amplitude or the power of the light wave coming to your telescope. But in radio astronomy, the atmosphere doesn't disturb the position of the wave. And so in radio astronomy, we get not only the strength of the light in the wave, we get the position of the wave. We call that the phase information. And because we've got both the position and the amplitude or the power of the light waves coming in, we can literally link together telescopes from all around the world. And so we can take a telescope in Hawaii, link it with a telescope in the Virgin Islands, link it with a telescope in Germany, and several telescopes across the US. And the bottom line is we wind up using computer and TV technology to build the equivalent of a telescope that has a mere 6,000 miles in diameter. Now you say, well, what about all the missing parts? Well, again, what we do in radio astronomy is we have these telescopes. Say we put together 15 telescopes around the world, and as the Earth rotates, you get a circle of information. But with each set, you get a different circle. And if you got 15 telescopes, you get 15 factorial circles. Let me break down the math for you. That's 15 times 14 times 13 times 12. So you get a lot of circles. And what this does is actually almost completely fill in. So you wind up, now this takes time. It takes many weeks of observations, but the bottom line is you wind up getting an image that would be like having a Hubble Space Telescope 6,000 miles in diameter. That can be done at radio wavelengths. And it took a telescope of that power to be able to image the black hole in the center of M87. And so, as you're probably all aware of, black holes are black because the gravity is so intense that once light gets close enough to the black hole, the light can't escape. And so once you get inside that distance, everything is black. And this is the first time that astronomers have been able to image what they call the event horizon of a black hole, where they got a telescope of such great power, they can actually resolve that little tiny disk where light can't escape. So a little donut you see there, that's the event horizon of the 6.5 billion solar mass black hole in the galaxy M87. You say, well, how do you explain all that bright light around it? Well, when the black hole is pulling in matter towards the center of that black hole, that matter gets converted into energy with 10 to 42% efficiency. And so these supermassive black holes, the region outside the event horizon, actually ranks as the brightest objects in the universe. Quasars, that's what a quasar is. It's a supermassive black hole that's sucking in matter towards its event horizon, where the energy conversion is so extreme we can see them out to great distances. Now, this is the image of the black hole, the event horizon in our galaxy. Now, it's a lot closer. It's only 26,000 light years away, but because the supermassive black hole is only 4 million times the mass of our star, the Sun, this was actually orders of magnitude more challenging for astronomers to image than the one in M87. Challenging for two reasons. The supermassive black hole is much, much smaller, literally about 2,000 times smaller, but the really big reason is it's not pulling in very much matter. Because it's not pulling in very much matter, we don't see very much going on outside the event horizon. And it took 4 years of observations for astronomers to come up with this image. And as you notice, it's still a rather fuzzy image compared to this one. Here we got a much more distinct image of the event horizon than what we have here. And astronomers are planning to continue to observe this to see what's going on. You'll also notice that you see some bright spots and dim spots around it. Astronomers are analyzing that, and bottom line, they've concluded the Milky Way galaxy is pulling in very little matter towards a supermassive black hole. And that's why you're all able to sit here today. If it was like what we see in other galaxies, then we would not be here. It might be possible at plants and trees, at microbes, but not human beings. But thankfully, we're living at a time in the history of our Milky Way galaxy where it's on a starvation diet. In fact, the analysis of this image is basically telling us the biggest stuff that's being pulled into the supermassive black hole of our Milky Way galaxy is no bigger than the medium-sized asteroids and comets that orbit about our sun. And so it pulls in one of those literally every few hours, but that doesn't cause radiation. That's a problem. Whereas if you're looking at M87 here, it's pulling in objects as big as stars and star clusters and giant molecular clouds. And when that happens, it throws out radiation that would basically sterilize not only its own galaxy, but all the galaxies around it. But that's not happening with our Milky Way galaxy. However, we do know that things were happening in the past, because this is an image of two gigantic X-ray bubbles coming out from the supermassive black hole at the center of our galaxy. But astronomers have very carefully measured the rate at which these bubbles of X-ray radiation are expanding. And it basically tells them that about 2 to 3 million years ago, our supermassive black hole was sucking in big stuff. And that's what caused these giant X-ray bubbles. But you only see two bubbles. And notice they're virtually perfect spheres. We don't see any structure. It's basically telling us nothing much has happened over the past 2 to 3 million years. And a detailed map is basically telling us over the past 100,000 years, our Milky Way's supermassive black hole literally has been on a starvation diet. So not much has been happening there at all. And if you want to read about this in detail, I actually wrote a paper that you can read for free online called Black Holes as Evidence of God's Care. If you put that title into a search engine, it'll pop right up. And it's a peer-reviewed paper, and I drew 3 astrophysicists who were atheists, and 2 of them wanted to reject the paper, but I had a chance to respond. What I loved about the journal, they made public the reviews of the 3 reviewers, and they also made public my responses. So you can read the reviews, you can read my responses, and you can see how the 2 eventually said, okay, we got to let this thing get published. So, but what I loved about the journal, they said, as long as the science is heavy, we're okay with you making a link with God. So we did make that link with God. But the bottom line is, our Milky Way galaxy has been quiet for the last 2 million years and extremely, extremely quiet for the last 100,000 years. And it's during the last 100,000 years that we humans have been on the face of the earth. What you can see from Genesis chapter 2 is that God created Adam and Eve sometime during the last ice age, because the text tells us that God created Adam and Eve and put them in the Garden of Eden. And the Garden of Eden is described as a place where the Tigris, the Euphrates, the Gihon, the Pishon come close together. Tigris and Euphrates are still flowing today. Why? Because they got ice and snow to feed the rivers. The Gihon, the Pishon were flowing during the last ice age. They're not flowing today because their store of ice and snow is completely gone. There is no snow or ice on the mountains of Havilah anymore. And there is no snow and ice on the mountains of Cush that were feeding the Gihon. So they're dry riverbeds. But we know where those dry riverbeds are, and the one location where those 4 rivers do come together is in the southeastern part of the Persian Gulf, which today is more than 200 feet below sea level, but during the last ice age, they would have been more than 80 feet above sea level. And so the last ice age, 15,000 to 120,000 years ago, this supermassive black hole has been extremely quiet for the last 100,000 years. Everything was timed for the entry of human beings. But this is where I want to finish with some of the new evidence, and that pertains to what's inside the local bubble. inside the local bubble, we have something called the local fluff. It's a new astronomical term, and you see that little yellow circle there? That's the local fluff. That little orange dot there represents where our solar system exists. So we exist virtually dead center in the local bubble and dead center in the local fluff. You say, what is this local fluff? Well, it began to form about 3 million years ago as a result of 1 or 2 local supernovae that funneled gas and dust into the local bubble's core. So the density of the gas and dust in the core of the local bubble is higher than it is elsewhere in the local bubble. And 200,000 years ago, the sun moved into the center of the local fluff. And so 3 million years ago, the local fluff forms. We call it the local fluff because it's a slightly higher, denser region of gas and dust. And 200,000 years ago, the sun moved into the center of that local fluff, which means that for the past 200,000 years, the local fluff has compressed the solar heliosphere. Now, the sun has an atmosphere. We call it an astrosphere because it's a star, astrosphere. And you're probably aware of Voyager 1 and 2 being sent out past Pluto. And one of the reasons why they maintain those spacecraft, they're trying to measure the edge of what they call a heliosphere. The heliosphere represents the distance from our star to the sun where the solar radiation is stronger than the cosmic radiation. And so cosmic radiation is pouring in towards the solar system. The solar radiation is moving out. The heliosphere is defined as that region where the two are in balance, where the incoming cosmic radiation is balanced by the outgoing solar radiation. But by being in the local fluff, what that local fluff did was compress the heliosphere, made it smaller than it was, and made it smaller by exactly the right amount so that the end result is it minimizes both the deadly solar radiation and the deadly cosmic radiation. This was all set up 200,000 years ago. So this is the part that's not in Design to the Core. Something I just recognized in my trip home from Hawaii, that we actually have another amazing time coincidence. At the very moment when the supermassive black hole in our galaxy was coming down to this extreme starvation diet, so that we had extremely little radiation coming out from the center of our galaxy, making our civilization possible, that coincided with the time that the sun entered the local fluff, where now we're in the center of the local fluff. We have a minimization of both the cosmic radiation, and see, we get cosmic radiation not just from the supermassive black hole at the center of our galaxy, but also from the various supernova remnants that surround the local arm in our Milky Way galaxy. And so 200,000 years ago, we entered that. 100,000 years ago, our supermassive black hole entered an extremely quiet phase. And now we have this local fluff and the local bubble giving us the optimal protection from radiation, gives us the optimal protection from gravitational disturbances. That's the local bubble. Local fluff gives us the optimal protection from cosmic radiation and solar radiation. So I'm going to stop there and take questions. But again, you can check more about this out in the Crater in the Cosmos. We're offering Chapter 15 for free, and likewise Design to the Core. And we'll take questions from the live audience and alternate with questions from the virtual audience. So we all set? Need 1 minute? Okay, we're trying to get the people. Oh, we got a question here from the live audience.
Yeah, come on. I'll bring the mic to him. Hang on.
Okay.
This is Dan.
I got 2 questions, sir. When you were talking about the black holes, what makes the hole pull itself into it?
Okay, what causes a black
Yeah.
hole to form?
Yes.
It's gravity, and if you've got a star that's massive enough, it was a fellow by the name of Schwarzschild almost a century ago who calculated that if you've got a star that ends its nuclear fuel burning phase with a mass greater than 1.4 times the mass of our star, the Sun, that mass will generate a gravitational force that's so strong that it forces the star to become a neutron star. And as it becomes a neutron star, if it's still greater than about 1.4, it'll continue on and become a black hole. And basically a black hole is a body collapsing under the force of gravity where nothing else can overcome that force of gravity, at least not for a long, long, long time. It was Stephen Hawking who calculated, well, black holes do not shrink forever. They basically shrink down to a point where the entire star becomes collapsed into the size of about a proton. And when it becomes that small, then quantum mechanics will generate forces powerful enough to overcome the force of gravity. And so black holes, if you wait long enough, become white holes, where everything that's been pulled into the black hole eventually will be blasted out. But you got to wait a long, long time. The bigger the black hole, the longer you have to wait. For the theoretically smallest black hole that can possibly exist, the wait time is 10 to the 66 years. So our universe is only 10 to the 10 years old. So
My second question, sir. When you explain how the sun was formed, as a Christian, you can tell somebody this is impossible unless it was designed. Just like the moon, how it was formed, and then how these planets relate to each other, and why the sun has heat.
well,
and flames.
this is what
See?
you'll see in both the book Designed to the Core and that online paper, Black Holes as Evidence of God's Care. Black holes are deadly objects. However, we need black holes to form. And typically how a black hole forms is you've got neutron stars that merge together, and two neutron stars are sufficiently massive that when they merge, they must become a black hole. But as neutron stars merge to become black holes, they produce half the elements that are heavier than iron. And so, for example, almost all of our uranium and thorium, almost all of our platinum, and about 30 other elements come from the merging of these neutron stars to become black holes. So there's no black holes, we'd have no uranium, we'd have no thorium. Without uranium and thorium, we'd have no magnetic field that would be protecting life here on planet Earth. We wouldn't have the plate tectonics. And by the way, several of the metals that are in your body that are crucial for you to exist come from the merging of neutron stars. So, hey, when you celebrate Thanksgiving in November, you might want to thank God for these merging neutron stars that became black holes, because you wouldn't have the amount of iodine and arsenic and other elements in your body that are essential for you to live. So, and then the fine-tuning goes beyond that. Our Milky Way galaxy, if it was a normal spiral galaxy, would have a supermassive black hole that would weigh in at about 140 million times the mass of our star, the Sun. For many reasons that I described in the book, its mass is only 4 million. We know of no other galaxy of the size of a Milky Way galaxy that's got such an extremely small supermassive black hole. But if we were like a typical galaxy, none of us would be here. We're only here because we live in a spiral galaxy that's as big as it is, with as tiny of a supermassive black hole that it has, and we happen to be living in that very small time window when our rather tiny supermassive black hole is on a starvation diet. And by the way, some people have asked me, well, when is that starvation diet going to end? Well, it could literally end any time. But so far, God seems to be making sure, because we do know that around our supermassive black hole is a huge cloud of asteroids and comets, a much bigger one than exists around our star, the Sun. And so far, it's only been eating small asteroids and comets. But if it starts eating big ones or a whole bunch all at once, that's really going to mess up your investment portfolio. Okay,
Okay.
question.
Online question from Doug McComb. Why do sunspots appear to be dark, and do they have any role in solar flares?
Okay, why do sunspots appear to be dark? Well, they're dark because they're cooler than the rest of the surface of the sun. They are hot, but they're typically about 1,000 degrees cooler than the surrounding solar area, which is why they look like they're black or dark. And what causes that cooling is the fact that there's a magnetic field disturbance in that part of the sun's surface. So instead of that part of the surface being all heat energy, it's a combination of heat energy and magnetic energy. And that combination of magnetic energy means that the heat energy will be less, and hence it appears to be dark. And because of the powerful magnetic fields that are associated with these sunspots, you do get flares. And incidentally, all stars have spots. For the sun, we call them sunspots. For other stars, we call them star spots. And we astronomers can actually detect and determine the degree of spots in other stars. And one thing we know is our sun is an exceptional star in that it doesn't have very many spots. And where it's super exceptional is that, yes, it has flares, but it doesn't have the super flares we see in other stars. In fact, you'll see one figure in Design to the Core where I show you the luminosity stability of our star, the Sun, and the second best star astronomers have found in our galaxy. And our Sun is 5 times more stable than the star that places second. So, but I can also share with you, we're in an extraordinary narrow time window when we're not getting a lot of nasty flares. Now, how many of you have ever seen the Northern Lights? Okay. I got to see them when I was on vacation in Canada back in August. So you get 24 hours notice. So if you go to the NASA website, they'll say, hey, there's a big flare that we just observed today, and it's heading in the direction of the Earth. Wait 24 hours, you're going to see Northern Lights if you happen to be at a fairly high latitude. It takes about 24 hours to hit the Earth. So now we get advance notice. And hey, if you got the money, you can grab an airplane and go to Iceland or go to Alaska and get to see the Northern Lights. Growing up in Canada, I saw the Northern Lights all the time. In fact, I saw them as a young astronomer. We considered the Northern Lights a nuisance because the Northern Lights at times would be so spectacular, we'd have to shut down our telescope and forget about our observations. Just ruined our attempts to look at stars and galaxies. But it was gorgeous to look at, an incredible light show. I actually did get to see the Northern Lights once here in Los Angeles. I think it was 1989, the same year that there was a flare that shut down the Quebec power grid. You could actually see a big red cloud up in the LA sky. It didn't move, it wasn't changing colors, it was just one spot. But hey, it was Los Angeles. But that's the only time I've ever seen it here in Los Angeles. Okay.
Hi, Hugh. Norm Helgeson. You've described a black hole as an object with such strong gravity that no light could be emitted from it. And yet you describe this jet being emitted by a black hole. So that seems to be some contradiction, or if you could explain that, that is...
Right.
Okay, thank you.
Well, Nora, I think you probably know the answer since you're a physicist, and that is that we're talking about nothing can escape the black hole's gravity inside the event horizon of the black hole. That jet was outside the event horizon. And outside the event horizon, the black hole is pulling matter towards the center of the black hole, But as it's approaching the event horizon, that matter gets converted into energy with high efficiency. And just before it hits the event horizon, the efficiency can be as high as 42%. And again, to give you a point of comparison, our sun converts matter into energy with 0.07% efficiency. So we're looking at something that's hundreds of times greater outside the event horizon. So if I were to go back here we go. Yeah, the event horizon is way inside that dot at the upper left. And the jet is outside the event horizon. And incidentally, you can see as you get a little further away from the event horizon, you actually get more intense radiation. So, got a follow-up?
Thank you. I'd like to make a note something also is that I saw Martin Schmidt, philosopher, an astronomer from Caltech, who observed the first evidence of these black holes back in 1960s. And it was a bright object in the sky, and it was later identified to be this black hole. So I just wanted to make that note of this man that was...
Well, Norm, I actually knew Martin Schmidt. His office was just a few feet from my office at Caltech. And yeah, he's down in the history books as being the first one to discover a quasar. And we discovered the quasar. Nobody at Caltech or anywhere else in the world could understand how come they were so energetic. Matter of fact, when Martin Schmidt came up with that discovery in the 60s, there were many famous astronomers who said these quasars cannot be inside galaxies. They have to be closer to us because the energy density is too extreme. At that time, they couldn't conceive of how you could get such extreme energy density. Today, we know if you've got a really big black hole that's pulling in lots of matter, you can get that extreme density, even in something that's as far away. So, but Martin Schmidt, to his death, held to the fact, hey, these really are in distant galaxies. I don't understand how we can get such extreme energy, but I know from my observations, they're not nearby. They really are in the cores of these galaxies. And at that time, nobody had a telescope powerful enough to see the galaxy. We could see the quasar, and people said to Martin Schmidt's face, they said, you gotta be wrong. You say that this is at the center of a galaxy, but where's the galaxy? We don't see the galaxy. Well, today we have telescopes powerful enough that we can see the galaxy, but the galaxy that houses these quasars are literally tens of thousands of times fainter than the quasar. So it takes a sophisticated instrument to be able to detect the faint image of the galaxy that's housing those quasars. And incidentally, that was part of my PhD thesis, was try to understand what explains the extreme energy density of these things. Today we know. Another one for
Okay, got an online question from Keith Wilson, New Zealand.
our New Zealand fan, right?
Previously, you mentioned a globular cluster that was oval due to a former central bar when it was a galaxy. Is this Omega Centauri?
Yeah, Omega Centauri is the largest globular cluster that's orbiting our Milky Way galaxy. It's got 10 million stars. The vast majority of globular clusters look spherical. The Omega galaxy or globular cluster is kind of an ellipsoid. So it's basically a flattened spheroid. And astronomers now believe that the Omega Centauri globular cluster is probably the core of a captured small dwarf galaxy. Because our Milky Way galaxy is capturing these tiny dwarf galaxies on a fairly regular basis. And so that's what most astronomers think is going on, because it's much bigger. Most globular clusters, we're looking at 100,000, maybe 200,000 stars, but the Omega Centauri, 10 million stars. So they're saying, hey, it's probably in a different category. And astronomers are trying to figure, well, how many of the globular clusters in our Milky Way galaxy are actually the remnants of the cores of captured tiny dwarf galaxies. And dwarf galaxies can be as big as 1%, the mass of our Milky Way galaxy, or as tiny as 0.001%. So it's quite a range. So that's ongoing research right now. And we had a star party years ago where we timed it in April because there's a week in April where the Omega Centauri globular cluster comes high enough above the Los Angeles horizon that you can actually see it. It's the brightest and biggest of the globular clusters, and if you're where Keith Wilson is in New Zealand, it's easy to see with the naked eye. But where we are, there's only 1 month of the year where it comes high enough that it comes above the horizon. But as we looked at it through my telescope, it was in the telescope eyepiece, it was about the angular diameter of the moon. That's how big it is.
Any questions from the audience?
Question here.
Yes.
Hi, Hugh. Bob Morankich. A question I've been wondering since we used to meet 100 feet from here is, I'm going to make a term. Is there such a thing as a black nova? In other words, a nova that expels enough of its matter and energy that it stops the rest of everything coming out of it from being visible?
Yes, we do. A nova is not a supernova. A supernova is a star that's so big that it blasts out so much of the stellar material that for a few months it shines as brightly as 100 billion stars. A nova is more than 1,000 times fainter than a supernova, but it's still such that people talk about guest stars, where you're looking in a particular constellation and a new star appears. It's a nova, and it'll shine brightly for a few months and then it disappears. So that's the difference between a nova and a supernova. And with both nova and supernova, you get a shell of stellar material that's blasted out from the star. And that shell will glow with light. So like with supernova, we refer to supernova remnants. You can't see the star that went supernova anymore, but you can see the remnant or the shell of material that got exploded out from the star. The same thing is true in novae. You can go to the NASA website and you can see images of the remnants of the nova stars. But if you wait long enough, the remnant will eventually dissipate because it's expanding. So the more it expands, the fainter it gets. And then eventually it expands and dims to a point where it just blends into the background of our Milky Way galaxy. So in our Milky Way galaxy, there's thousands and thousands of remnants of supernova and also nova. But there's probably many more than that because eventually it just blends into a background of a previously nova and supernova eruptions. But yeah, you see the remnant long after you can't see the star. Now, if you're close enough to the nova, you can actually see the star because it'll basically be a cooling down white dwarf. And so, and there are no black dwarfs in the universe. A black dwarf is an exploded star or a dying star. Our sun will become a white dwarf after it runs out of nuclear fuel. But when it becomes a white dwarf, it will continue to be visible for about 1 trillion years. So that's how long it takes for a white dwarf to finally cool off and become black. And because the universe is only 14 billion years old, there are no black dwarfs anywhere in the universe. The universe is not old enough for stars to completely cool down. And so it's kind of like an analogy of an open fire where you got embers on the open fire. Notice that those embers will glow, even though it's no longer burning, it will glow with light for many hours thereafter. But typically, if you wait a day or two, those embers become completely black. With the case of stars, not enough time has yet transpired for them to become black. Matter of fact, we would predict that a white dwarf, if you wait long enough, will become yellow, and then orange, and then red, and all the white dwarfs are still white. They're either blue or white. So not enough time has even transpired for a white dwarf to become yellow in its color. Got another question?
Oh, yeah, we got plenty.
Got a lot, okay.
Yeah. This one's from Mark Wilburn. I'm a new Christian brought to the faith through the science to faith connections taught by Dr. Ross.
All right.
And he wants to know if you could tell him some resurrection verses that are in the Gospels.
Some resurrection verses that are in the Gospels. Well, I'm not going to be able to cite the exact verses, but what's interesting is you go through the Gospels and the epistles. The epistles are the letters written by the apostles after Jesus was raised from the dead. But you've got Romans 8:1, I think it is, which makes the point that the Father raised Jesus Christ bodily from the dead. You've got a verse where it says the Holy Spirit raised him bodily from the dead, and Jesus claims to have raised himself bodily from the dead. And we're also told there's only one resurrection of Jesus from the dead. So this is a New Testament demonstration of the doctrine of the Trinity, where God is one essence, which means one mind, one purpose, one set of character attributes that they all manifest, but it's manifested as three persons, Father, Son, and Holy Spirit. So all three members of the triune God take credit for raising Jesus Christ bodily from the dead, yet there's just one resurrection. Now, maybe you discerned something else in the question he was asking?
No, it was just that simple. So he just wanted to know verses that related to
Well, at the
resurrection.
end of all four Gospels, you'll see a chapter which gives details about the resurrection of Jesus from the dead. My favorite are the one you see in the Gospel of John, because John wrote his Gospel after the other three Gospels were written, and he kind of explains why he wrote the Gospel of John. He says, I'm writing this so that you will know that Jesus of Nazareth indeed was God. So he says, and he doesn't repeat much of what's in the other three Gospels. They're basically telling the story of his life. What you see in the Gospel of John is that he selects out those parts of Jesus' life that really establish that he is God. He's not just a great prophet, he is God. And so a lot of the miracles that Jesus performed that you see in Mark, Matthew, and Luke are not described in John. But what you do see described in John are those miracles that the Jews as a nation said, these are miracles no prophet can perform, only God himself can perform. And so we got the story, for example, of Jesus raising Lazarus from the dead after he had been dead 4 days. Because they said, yeah, Elijah could he raised the widow's son from the dead, but that widow's son had only been dead a few hours. Case of Lazarus had been dead for 4 days and 4 nights. And it's in the Gospel of John where Jesus says in chapter 8 that he is Yahweh. He takes the name Yahweh. And that's something you see in the book of Jeremiah, is that both God the Father and God the Son take the name Yahweh. And that's what caused the religious leaders to say, we have to stone this guy to death. He's claiming to be God. But Jesus is making the point, I really am who I say I am. I really am God. So that's the Gospel of John. And the Gospel of John also describes events of the resurrection that are unique to the Gospel of John. It describes, for example, how he had a rich man's burial and how he was encased in rosin and cloth and linen cloth, and that the rosin and linen cloth added up to a talent weight, more than a talent weight. Well, the smallest talent was 75 pounds. Typically a talent is 100 pounds, so it's basically saying at least 75, maybe more than 100 pounds of rosin and linen surrounded the body of Jesus, and then there was a headpiece. And what we see recorded in the Gospel of John is that, when you got Peter and John coming into the empty tomb, they see the grave clothes and they immediately believe in the resurrection. and a number of Bible scholars have pointed out, what they most likely saw was the equivalent of 3 inches thickness of fiberglass around the body. Because if you got 75 to 100 pounds of linen cloth and rosin, it's going to set around the body of Jesus like about 3 inches thick of fiberglass. And said if what they saw was a body cast with no cuts or holes in it, they would immediately recognize the only possible explanation is that he supernaturally escaped this case that was around him. And they looked at it and immediately believed. So those are details you see in the Gospel of John. But put together all 4 of the Gospels, you get a really detailed picture. Yes?
My name is Gary. I've been interested in exactly what you brought up because the Synoptic Gospels just basically say that there was a shroud placed over Jesus rather than this whole burial clothes. How do you account for that?
Well, there's great controversy about the Shroud of Turin, and you're probably aware that they had the Jet Propulsion Laboratory here in the LA area, carbon-14 dated, and there's controversy about the date, because the date came back 13th century AD, and they said, well, that's the century when there was quite a huge black market for artifacts related to Jesus, and therefore they concluded the Shroud of Turin likely is a forgery, but it's a very good forgery, so good that some people concluded perhaps they even crucified someone to death in order to get the details as precise as they did. But they said, given what we saw in the 13th century AD, that's not beyond the possibility. However, others have said, look, the error bar in that carbon-14 date is suspect, and I would agree. Carbon-14 only gives you reliable dates within about a factor of 7 of the half-life. The half-life is 5,715 years. You divide by 7, and that means that we're looking at 13th century. You're outside the range where you're going to get a reliable date. But then other people at JPL said, well, if you think it's 2,000 years ago, if it was, we would have gotten a high precision date, because that's well within the range of carbon-14. We didn't get that. They said, well, I think the problem is you took it from the wrong piece of the shroud, because maybe the shroud is a combination of a garment material from 2,000 years ago and 1,300 years ago. And the response of the team at the Jet Propulsion Laboratory was, well, give us another piece of the shroud. We'll do another test. And if you don't think 4 inches is big enough, give us 8 square inches, and we'll be able to give you a reliable date. Well, so far, the people who own the shroud haven't been willing to have a second test performed. But you're bringing up a good point. If indeed 75 pounds of rosin were impressed into the linen cloth, where's the evidence of all this rosin? We don't see it with the Shroud of Turin. And other people have said, well, we got an explanation for that. There was both a shroud plus the body cast. But now you're getting into significant speculation. Bottom line is this: we don't need the shroud to prove the resurrection of Jesus from the dead. If we do come up with evidence that it is, that's a bonus. But we have far more compelling evidence for the bodily resurrection of Jesus from the dead than anything we're going to get, no matter what turns out about the shroud. So, me personally, I'm saying I'm not going to make a commitment about the shroud until we got more data. Okay. We got it. Dan? Pardon me?
The pizza man talked to me and said he's going to come Sunday with a pizza.
All right, next Sunday.
Okay.
We got special pizza treats coming. So
Pizza next week, okay.
pizza next
It's
week.
announced now.
All right.
Dan, courtesy of Dan. I think we only have time for one more
Yeah,
question.
one more question, then we'll
All
wrap it
right.
up.
This one's from Susan Lamb. Has anyone made a map of the universe showing how possibly it looks now at this moment, like stars being burnt out or gone nova, or new stars and where galaxies are now?
Yeah, good question from Susan Lambeau. Do we astronomers actually project what our local part of our Milky Way galaxy is going to look like in the future, or our whole galaxy will look like in the future, or distant galaxies. A lot of that work is actually being done. Something I mentioned in Design to the Core is that we can look at a galaxy, say 3 billion light years away, which means we're seeing it 3 billion years ago. And if we get a detailed enough map, we can use that to project what that galaxy looks like today. Now, where you may have seen some of that on the web is that, for example, if you look at the Big Dipper, all the stars in the Big Dipper are moving relative to us. And so you can go after lunch today, go online, look at Big Dipper. You'll probably be able to pop up a map that'll show you what the Big Dipper looked like 10 million years ago, what it looks like today, and what it will look like 10 million years from now, and 50 million years from now. It looks like a dipper now. It didn't look like a dipper 10 million years ago, and it won't look like a dipper 10 million years from now. Obviously, we can do that with higher precision on objects that are closer to us in space and time. So the more distant and the farther back in time you go, the more challenging that it is. But what's amazing to me is that, and this is mentioned in Design to the Core, is that we can make these kinds of projections even from galaxies that are 10 billion light years away. We can look at them, look at the galaxies in their vicinity, and make at least a crude estimate of the development of that galaxy from 10 billion years ago, which is how we're seeing it now, to what would be approximately looking like today.
Okay, Hugh.
Okay.
I think we're done. So can you close us in prayer, please?
I'll be happy to do that. Father in heaven, we thank you for this day. Thank you, Lord, for giving us the special privilege of having both the book of nature and the book of scripture in the detail and the research that exists today. Thank you for all the scientists and theologians that have been researching this for millennia. And Father, I pray that we would all get great joy of diving into this. Thank you that you invite all of us to be theologians. You invite all of us to be scientists. Lord, may we be greatly enriched as we study your books, and give us many opportunities to share what we discover with people that we know, our friends, associates, and friends, and workers. In Jesus' name, amen. Thank you. Thank you.
Did you bring one of your books for sale right now?
We don't have any books here, but we're talking about setting up a book.